In this video, we're going to consider electromagnetic energy. Electromagnetic energy travels in waves. The electromagnetic spectrum lists all of the waves in order from shortest to longest wavelength, and this is in your reference table on page 14. When electromagnetic energy comes in contact with a material, one of 5 things can happen. The first thing is it can be transmitted, which is when it just passes through a medium unchanged. The second thing is it can be refracted, which is when the energy passes through a medium and it changes direction, and this is due to the fact that it's going through a material that's a different density, and so the energy is slowed down and it bends. The third thing that can happen is that the energy is reflected, which means that it bounces off of a flat surface and it's unchanged. The fourth thing is that the energy can be scattered, and that's when energy bounces off the particles in a medium and spreads out in all directions. Now this is similar to reflection, except instead of bouncing off of a flat surface, it's going in many different directions. And the last thing is that the energy can be absorbed, and that's when the energy is taken into the medium. Now there are some characteristics of a material that will determine whether it's going to be a good reflector or a good absorber. Good reflectors have light colors and smooth textures. Good absorbers have dark colors and rough textures. Materials that are good absorbers of electromagnetic energy are also good radiators of electromagnetic energy. This means that a dark colored object, for example, will heat up quickly in sunlight, but it will also cool off quickly after sunset because it rapidly radiates that electromagnetic energy back into the environment. Energy from the sun is called insolation, not to be confused with insulation, which is the pink stuff that is in most of our walls and attics. This diagram illustrates what is in sunlight. On the x-axis, you can see that we have taken a portion of the electromagnetic spectrum, and that goes from ultraviolet, visible light, and infrared, and that's the portion of the electromagnetic spectrum that I've put in a yellow rectangle around. On the other axis, you can see the intensity of radiation, which is another way of saying the amount of energy, and the graph shows how much energy is in which kind of wavelength. And you can see that most of the sunlight is on the shortwave side of the electromagnetic spectrum, and that's the part that I've circled with a red circle. Now, of that shortwave radiation, this diagram here breaks down how much of it actually reaches the Earth, because the sun releases a lot of energy, but not all of it reaches the Earth. The green portion of that is the insulation that reaches the Earth, and that's about 51%. The red portion is the insulation that never reaches the Earth, and that's about 49%. So only about a little more than half of the sun's energy actually reaches the Earth. Now the question is, where does all that energy go? Well, about 47% of it reaches the Earth and is absorbed, and about 4% of it reaches the Earth but is then immediately reflected back into space. So that's the 51%. 23% of it is absorbed into the atmosphere, into clouds. 26% is bounced off of the atmosphere into clouds. The ozone layer is a very thin layer of atmosphere, and it's part of the stratosphere. And it's so thin, it's about the thickness of a penny. And much of the sun's ultraviolet radiation is reflected back into space by the ozone layer. This is really significant because ultraviolet radiation from the sun contains a lot of energy in that wavelength, and that can be harmful to living things on Earth. The intensity of insolation varies with the angle of the sun overhead in the sky. This is illustrated using a flashlight and a piece of paper. In this diagram, both flashlights radiate the same amount of energy, but the light from the overhead flashlight is more concentrated, and you can see that small disk of light where the flashlight is striking the paper. At a lower angle, the energy is spread over a greater area, and you can see that larger disk from the flashlight on the right on the paper. The light hitting at an angle is less concentrated, so every part of the paper that's struck by the low angle flashlight receives less energy. In this diagram, we can see the same thing is true with the sunlight striking the Earth. At low latitudes, they receive direct vertical rays from the sun, and so they have a higher concentration of energy, and that's why it's warmer in low latitudes. In high latitudes, the angle of insolation is a lower angle, and so the energy they receive from the sun is less concentrated. The energy is spread over a larger area, so the energy per unit area decreases, and that's why it's colder at polar regions.